My dear friends, welcome to Rajashekhar classes on applied data science with Python. This is lecture number 605. In this lecture, we will try to understand convolutional layer in neural networks. We understand these three operations: convolution, padding, and strides. Given that we understand these three concepts, now we can define how a convolutional layer in neural networks. Remember, how does a multi-layer perceptron look like? How does one layer in multi-layer perceptron looks like? We have layer of neurons, literally, isn't it? If you observe a layer in multi-layer perceptron, you can see layer of neurons. You get inputs from the previous layer, isn't it? Let's assume this is layer 2. What is layer 2? Layer 2 is this one is layer of neurons, isn't it? This is layer of neurons. Yes. This is layer 2. It could be I'm specifying layer 2. It could be any layer. You get inputs from the output of previous layer, isn't it? Just see, this is my previous layer. This is my previous layer. I am getting inputs to layer 2. These inputs are the outputs of previous layer. That's what I am saying, isn't it? Let's assume there are bunch of outputs. Let's assume there are bunch of outputs from the previous layer. Again, remember, this could be, let me say, this could be this layer. I am specifying about this particular layer. This could be an input layer, or it could be previous layer, isn't it? Given this layer in the sense, now given this layer 2, we are doing fully connected layers here, isn't it? Just see, FC means what? FC means fully connected. And then apply an operation on top of it. We output this, isn't it? Just what is this? Before we do it, we have two steps. What is my first step? My first step is, given all these inputs, let's call the input as X. What is my X? X is my input. Whatever the input, whether it is raw input or it's an input from previous stage, we have bunch of weights corresponding to each neuron. We are computing W transpose X as Z, isn't it? What is my Z? Z equal to W transpose X. Z is defined as W transpose X, and then we compute. What will we do? We compute activation units like ReLU on top of Z. Means you are applying ReLU activation function on Z. This becomes the output. What is my output? My output is Y. Y equal to ReLU on top of Z. Let me call this as Y. So for any neuron, the inputs from the previous layer are called X. The weights are called W. Z is basically the component wise multiplication followed by addition. This is nothing but, what is this? This is dot product. What is this? W dot X, which is nothing but component wise multiplication followed by addition. So you compute Z and then apply ReLU on top of it. Then it becomes Y. What is my Y? Y equal to ReLU on Z. This become input to the next layer. What is my Y? Y is nothing but ReLU on Z. This Y is input to the next layer. Next layer in the sense, what is next layer? Now you may have, I can say this is layer 3. Next layer in sense, yes, your Y is input to the layer 3. This is how your multi-layer perceptron looks like. Let's understand how a convolutional layer looks like. So one of the key things, just see, one of the key things, let's not forget this, one of the most important things, why are we designing the convolutional layer? That's important. Why are we designing the convolutional layer? We are designing convolutional layer because we are biologically inspired by the architecture present in mammalian brains like V1, V2, V3, so on, extra, based on the biological inspiration from visual cortex of cats, monkeys and humans. This is a core idea, how a convolutional layer looks like. So we know that within V1, that's a primary cortex, isn't it? We know that within V1, that is primary cortex. That is primary cortex means visual cortex. There are multiple edge detectors in the human brain, and we know that one edge detector corresponding to one kernel, which means if you want multiple edge detectors, create multiple kernels, isn't it? You need multiple kernels, or you need multiple kernels or multiple filters. I can say kernels or filters. Some people call them as filters. Let's call them as kernels for simplicity. Now the fun part is this: how should be these edge detectors or kernels be? So in convolutional neural network, remember, in the classical image processing, people come up with specialized kernels, isn't it? We saw the Sobel kernel, isn't it? Many other types of kernels. CNN will say, let's learn the kernel matrix using back propagation. Let's just learn it. So the way it looks is, in your classical multi-layer perceptron, your unknowns are W, isn't it? In your multi-layer perceptron, you learn your weights, you learn your W's. Given you will learn your weights, given inputs and outputs, isn't it? In CNN, in the context of CNN kernel, in the context of CNN, you learn your kernels. Yes, in CNN, you learn kernel matrices. This is important. In the context of CNN, what's happening? You learn your kernel matrices because they both are which are similar. In the context of CNN, we learn kernel matrices, isn't it? They both are very similar. Means weights and kernels are similar. Your weights in multi-layer perceptron, or classical multi-layer perceptron are similar to kernel matrices in convolutional neural networks. Remember, in your multi-layer perceptron, what are you doing? Taking a dot product between weights and your input vector. That's important, isn't it? In multi-layer perceptron, what you are taking dot product between weights and your input vector. That is W transpose X. Just try to recall what we discussed in MLP lectures. In convolution, what are you doing? We are taking the input image and convolving the kernels, isn't it? Taking the input image and convolving the kernels. Kernels can be thought of weight matrices, isn't it? What are the kernels? You can treat kernels as weight matrices, and we will learn these kernel matrices. So kernel matrices is exactly do the same thing that weights do. That's important. Kernel matrices do exactly same thing that weights do. There are some differences that we will understand. So the way we design one layer in convolutional neural network is like this, isn't it? Let's assume I have an input image here. Let me assume I have an input image here, a color image, let's say, which is of size n cross C. C means channels. We already discussed this, isn't it? I have one kernel here, let me say, which is, let's say, K cross C. When I convolve these two, just let me apply convolution operator in between these two, I get one image which is of size n minus k plus 1 into n minus k plus 1. If I don't do padding and all of that, this is simple convolution. Now, instead of one kernel, let's call this is kernel K1, isn't it? Instead of one kernel, if I have two kernels, isn't it? What happens? This will take this as input. Let's call this K2. K1 is first kernel, K2 is second kernel. This kernel will result in other image which is of size, let me say, second kernel is generating an image of size n minus k plus 1 into n minus k plus 1 size. If I have three kernels, this is first kernel. For first kernel, I am getting an image of n minus k plus 1 into n minus k plus 1. For second kernel, I am getting another image of size n minus k plus 1 into n minus k plus 1. If I have three kernels, I get three images here which is of size n minus k plus 1 into n minus k plus 1. Probably this kernel K1, what is the function K1 is doing here? Horizontal edge detection. Probably kernel K2 is doing, kernel K2 means second kernel is useful for vertical edge detectors, isn't it? To detect there may be another kernel which may detect edges with 45 degrees. So different kernels could learn different weight matrices. Instead of hard coding them as Sobel kernel or anything, let's learn the kernel weights from the data given our original data set capital D equal to xi comma yi. Based on the problem that we have to solve, let's learn kernel weights, kernel matrices, just the way we learned in multi-layer perceptron. With the way we learned weights in multi-layer perceptron. Just I will repeat. We have to, what you have to do, we learn the kernel weights, learn the kernel matrices, just learn the kernel matrices just the way we learned weights in the multi-layer perceptron. In the context of multi-layer perceptron, we learn weights. In the context of convolutional neural networks, we learn kernel matrices, isn't it? That is the important, isn't it? That is the important connection. That's the important connection. Kernels exactly works like weights in multi-layer perceptron. That's important, isn't it? Except that you could have multiple kernels, isn't it? So imagine if I have matrix, if I matrix here, n cross C matrix here. If I have an input which of size n cross C, let's assume I have one more third kernel. Third kernel means K3, isn't it? Which is again size K cross C. Let's call this kernel as K3. This is also results a third image, isn't it? Now I can stack all of these images. Just see now what's happening here. K1 is kernel 1. I am applying on n cross C image. I am getting n minus k plus 1 into n minus k plus 1 C size image, n minus k plus 1 into n minus k plus 1 size image. That is image 1. Just see. Here I am getting image 1 by using kernel K1. Here I am getting image 2 by using kernel K2. Here I am getting image 3 by using kernel K3. This kernel may be something like a Sobel horizontal edge detector. This may be Sobel something like Sobel vertical edge detector. This kernel may be a kernel which detects an edge with 45 degrees. Just I request all of you to go through this lecture. If you have any difficulty, please go through this lecture once or twice. Why? Because this lecture is very important. One thing you have to understand here, in the context of multi-layer perceptron, we used to learn weights. In the context of convolutional neural networks, we used to learn kernel matrices. Thank you very much.